If you want an AI job in 2026, stop memorizing papers. Seriously, stop. In 2023, you could get hired by Google or Meta just by explaining how a transformer works. You could draw the attention mechanism, write out the softmax formula, and you were hired. That was the research era. But look around, it is 2026. The industry has shifted. We aren't just building models anymore. We are engineering systems. Recruiters at MAANG do not care if you can derive backpropagation by hand on a whiteboard. They care if you can ship a model that doesn't hallucinate, doesn't crash production, and costs less than a fortune to run. We have moved from model builders to system architects. In the next 30 minutes, I am going to walk you through the exact interview loop for an L4 and L5 AI engineer role in 2026. We are going to cover the live coding that trips everyone up, the new system design questions focused on inference scaling, and the agentic evaluation questions that everyone is failing right now. Put your phone away, open your IDE, let your TMs get you hired. Before we look at the specific questions, we need to understand the battlefield. The interview process is split into 4 distinct rounds, and if you are using prep guides from 2024, you are preparing for a war that ended 2 years ago. Let's look at the new hierarchy of needs for an AI engineer. At the bottom, we still have coding and algorithms. But listen to me carefully. This is not just leet code. They aren't going to ask you to invert a binary tree just for fun. They are going to ask you to write high-performance Python that handles data pipelines. Can you write a tokenizer? Can you optimize a data loader using multiprocessing? If you can't handle asynchronous data streaming, you won't pass the phone screen. The next layer is system design. This is the killer. In the past, we asked you to design YouTube recommendations. That was vague. Now, the questions are specific. Design a multimodal RAG pipeline with sub-200 millisecond latency. The complexity has exploded. You need to know about vector databases, KV caching, and speculative decoding. And finally, the top layer, the one that catches everyone off guard. Product sense and safety. With AI regulation tightening globally, if you cannot explain how you align a model, how you prevent jailbreaks, or how you measure harm, you are a liability to the company. I have categorized the 6 types of questions you are guaranteed to see. We are going to go deep on each one. LLM-as start with the one that filters out 50% of candidates immediately. The large data problem. Let's look at the first problem type. Imagine the interviewer shares their screen and says, "We have a 50 terabyte dataset of text logs. It does not fit in your RAM. I want you to write a PyTorch DataLoader that streams this data efficiently for training. Oh, and I want you to shuffle it." Most juniors panic here. They try to use standard file reading or, God forbid, pandas.read CSV. That is an instant fail. Your computer will crash. The keyword here is stream. We need to use Python generators. Lita warno TM write this out. We are going to define a class called streaming dataset. Now, pay attention. We are inheriting from iterable dataset, not the standard map style dataset. Why? Because with a map style dataset, we need to know the index and the total length. With a 50 TB stream, we might not know the length. Inside this class, we define the maanator method. This is where the magic happens. We are not loading the file into a list. We are opening the file, and then we are using a loop to read line by line. We use the yield keyword here, yield line. This turns our function into a generator. It ensures that at any given millisecond, we only hold a single line of text in memory. This is how you process infinite data on a tiny laptop. But wait, the interviewer asked for shuffling. Think about it. How do you shuffle a deck of cards if you can only see one card at a time? You can't. This is a trick question to test your engineering common sense. You cannot achieve a perfect global shuffle on a stream without infinite memory. So, what do we build? We build a shuffle buffer. Here's how I code it. I create a list called buffer. As I iterate through my generator, I don't yield the data immediately. Instead, I fill this buffer until it hits a capacity of, say, 10,000 items. Once the buffer is full, I pick a random item from the buffer, yield that one, and then replace it with the next new item from the file stream. This gives us a pseudo shuffle. EOS TM-ES local randomization. It breaks the correlation between consecutive samples, which is usually enough for training neural networks, but it doesn't require loading 50 TB of data. If you can write this logic was generator plus shuffle buffer live in 10 minutes, you have proved you understand how data actually moves through hardware. Now, let's move to the second category, model debugging. In this scenario, you aren't writing code from scratch. The interviewer hands you a graph. It TM's a training loss curve. It goes down nicely for the first few epochs, and then suddenly, boom, it spikes up. Or worse, the line disappears and the value becomes NaN, not a number. They look at you and ask, what happened, and how do you fix it? Do not guess. You need to debug this systematically. First, let's talk about the spike. The loss was decreasing, which means the model was learning, then it jumped. This is almost always the exploding gradient problem. The model took a step so large during the update that it overshot the value of the loss function and landed somewhere chaotic. How do you fix it? You tell the interviewer. I would implement gradient clipping. In PyTorch, this is clip your grado yes norm. It effectively puts a speed limit on how much the model changes at every step. But what if the loss goes to NaN? That means a mathematical error occurred. Maybe you divided by 0. Maybe you took the log of a negative number. But in 2026, the most common reason for NaN is numerical instability due to mixed precision training. We are all training in FP16 or BF16 to save memory, but 16-bit numbers have a limited range. If your gradients get too small, they vanish to 0. If they get too big, they turn into infinity. If you look the interviewer in the eye and say, I would check for numerical overflow in the mixed precision scaler, and I might switch to BF16 because it has a wider dynamic range than standard FP16. You have just won the round. You showed you understand the hardware, not just the math. Now we arrive at the boss level, system design. Here is the prompt. Design the inference architecture for a Llama 4 level chatbot that needs to serve 1 million concurrent users with low latency. This is not about training. This is about serving. We start with the basics of a load balancer, obviously, but the core of your answer must focus on the GPU optimization. You cannot just load the model. You need to discuss KV caching. Explain to the interviewer, look, an LLM generates tokens one by one. For every new word it generates, it has to look back at the entire history of the conversation. Recalculating the attention map for the whole history every single time is wasteful. So, we use a KV cache. We save the key and value matrices of the past tokens in GPU memory. We only compute the new token. But here's the trade-off, and you must mention this. The KV cache eats up GPU VRAM aggressively. This leads you to the next concept, paged attention. Just like your operating system breaks RAM into pages to handle multiple apps, we break the KV cache into blocks. This allows us to handle memory fragmentation. If you mention paged attention or VLLM, you demonstrate you know the modern serving stack. Finally, to really impress them, bring up speculative decoding. You explain, running a massive 400 billion parameter model is slow, so I will put a tiny, cheap draft model in front of it. The draft model guesses the next 3 words very fast. Then the big model runs once to verify them. If they are correct, we just saved ourselves 3 expensive forward passes. This architecture argues KV cache, paged attention, speculative decoding is the standard for 2026. Draw this flow on the whiteboard and you pass. In 2023, we looked at accuracy numbers. We looked at a BLU score. In 2026, that is useless. We are building agents with AI that uses tools, searches the web, and executes code. How do you evaluate an AI that calls an API? There is no ground truth text to compare it to. You need to talk about LLM-as-a-Judge. This is the industry standard now. You build an evaluation pipeline where a highly intelligent model, like GPT-5 or a heavy Claude Model S, acts as the teacher grading the student's homework. You design a pipeline that verifies 3 specific metrics. Faithfulness. Did the model hallucinate information that wasn't in the source text? Context recall. Did the model actually find the relevant data in the documents provided? Tool use accuracy. When the user asked for the weather, did the model generate the correct JSON format to call the weather API? If you are asked to design a RAG system and you do not draw an eval loop that runs automatically on every code commit, you are failing the product sense portion of the interview. They want to know that you can sleep at night knowing your model isn't breaking in production. Lee-Tide URTMs simulate the pressure. Let's say you just designed that beautiful architecture we talked about. You are feeling good. Then the interviewer throws a wrench in the gears. They say, okay, nice design, but we just lost 30% of our GPU capacity due to a budget cut. We can't afford the H100s anymore. How do you keep this system running without making the user wait 10 seconds for an answer? This is the constraint question. There is no right answer. There are only trade-offs. Here is how you handle it. You offer options. Option 1, quantization. You tell them, we can compress the model weights. We move from 16-bit precision to 8-bit, INT8, or even 4-bit, INT4. We might see a 1% or 2% drop in reasoning quality, but we will reduce our memory footprint by 3x or 4x. This fits the model on cheaper cards. The interviewer might push back. But this is for a medical application, we can't lose accuracy. Okay, pivot to option 2, distillation. In that case, we can't just compress the weights. We need to train a smaller student model to mimic the teacher model specifically on medical data. We keep the domain intelligence, but we shrink the parameter count. The goal here isn't to solve the problem instantly, it's to show that you have a toolkit of solutions. Quantization, distillation, pruning, and you know when to use which one. You cannot learn all of this overnight. If you try to cram this in a weekend, you will burn out. You need a plan. Here is an 8-week roadmap to get you from reader to architect. Weeks 1 and 2. Focus on Python proficiency. Do not just solve LeetCode. Learn how to write generators, decorators, and use the multiprocessing library. Understand how Python manages memory. Weeks 3 and 4. Now, do the algorithms. Focus on graph and tree problems. Why? Because neural networks are just big graphs. If you understand graph traversal, you understand backpropagation. Weeks 5 and 6. This is the most important part. Build one complex project. Do not build a wrapper around the OpenAI API. That's too easy. I want you to fine-tune a llama model using lower A on a custom dataset, and then, this is the key, build a custom evaluation pipeline for it. Show that you can improve the model, not just use it. Week 7 and 8. System design mocks. Watch videos like this one, pause them, and try to draw the architecture yourself before seeing the solution. The bar has been raised. But that is actually good news. It is good news because it means the lazy applicants, the ones who just memorized a few definitions, are gone. They can't compete anymore. If you build the systems we talked about today, if you understand the data loading, the quantization, the evaluation pipelines, you won't just get an interview. You will be the one dictating the salary. I have put the code snippets for the data loader, the shuffle buffer logic, and the system design diagrams we covered today in a repository. The link is in the description. But I want to know who is really serious. Go to the comments right now. Comment the word architect and tell me which company you are gunning for in 2026. Yeah, you told. Going to pick one person from the comments to do a live one-on-one mock interview with next week. Stop reading, start building. OutTM, I'll see you in the next one.